All right. Okay, good morning, friends. Gentle reminder that homework 1 is due tomorrow, 11 o'clock in the evening. So what are we doing today? So the plan for today is to complete the proof that we kind of left off incomplete in the last class. Well, I didn't do it properly, so I'll do it now. And maybe just investigate a couple of more properties of trees and then start something new. Okay, so let us revisit that proof, right? So what was the claim that we were trying to prove? We were trying to prove that the graph G has a cycle if and only if there exist two vertices A and B such that G contains at least two paths from A to B. Okay, so one part of the if and only if was easy. Suppose you had a cycle, then it was easy to construct two vertices and two paths between them using that cycle. Okay, so the other part, right? So suppose the graph G given to you has two paths between some pair of vertices. Okay, so then we said that, okay, let len of P denote the length of the path P, which is the number of hops that you take in the path, right? And then we define the set S to be the set of all numbers, right, of the form length of P plus length of P prime, where P and P prime are two distinct paths in G with the same pair of endpoints. Okay, so we are given that S is non-empty, right? That's what is given to us, and therefore by well ordering principle, S has a minimum element, say M, right? So this is what we had last time, um, right? So therefore there exists vertices xy and paths p1 p2 from x to y of total length M, right? And then we denoted those paths by p1 and p2, p1 and p2, which is x v1 v2 up to vk and y, and x w1 w2 up to wl and y. And then we said that the total length of the path is k plus l plus 2, which is equal to m. Okay, now because these are paths, right? So we know that v1 through vk are all distinct and they are different from x and y. Similarly, w1 through wl are all distinct and different from x and y. Is everything okay up to this point? Any quick questions before we go ahead, Shrimanti? Shrimanti, your hand is up.
Sir, sir, one thing, sir, when you said that, am
Yeah.
I audible?
Yes, yes, you're audible.
Okay, sir, when you said that I equal j equal 1, sir, I thought that can we include the condition that the second vertex in the paths P and P dash should be different?
What I equal to j equal to one you're talking about?
So the case that the previous day you said couldn't be resolved.
Acha, acha. So we are going to resolve it now, and then let's resolve it, and then if you have a question, you can ask. Is that okay?
Yes, sir, no, I'm not asking questions. Sir. I'm saying if we want to resolve it, then can we say that in the second set S, we include a condition that P and P dash are distinct paths in G with the same
Uh,
endpoints, and the second vertex in those paths are different, for sure.
I am not sure what exactly you are trying to say. So, Shrimanti, it's best if we try to investigate what you are trying to say after we finish this proof of. Is that okay? So, my question is,
Okay.
as far as everything on this slide is concerned, is that okay? That's okay, no, Shrimanti?
Yes, sir.
Okay, cool. Cool. So now let us try to finish off this proof. So now what? Now if we can somehow prove that these VIs are all different from the WIs, then we are done, because we can take the following, we can construct the following cycle: X, V1, V2, Vk, Y, followed by WL, WL minus 1, blah blah blah, W1, X. Right? So we are going to prove that each VI is different from each W. Okay. So, right, so let me just write it over here. We claim that, or let me say it this way: x, y, v1 through vk, w1 through wl are all distinct. Okay, so why are they distinct? So suppose they are not distinct. So let us get rid of the messy part of this. So suppose they are not distinct. Okay. Suppose not. Right, then where can a collision happen, right? So we know that x and y are different from v1 through vk, x and y are different from w1 through wk, so therefore we must have k and l both greater than or equal to 1, right? And moreover, there exists ij such that vi is equal to wj, and let's call that common vertex to be z. Okay, so fine. So now let us consider the yeah. So let's draw a little diagram over here. Right. So you have x, you have this vertex vi equal to wj equal to z. You have this vertex y, and then there is something happening, some mess happening over here. I don't know. There could be a lot of things, a lot of possibilities. Something.
Sir, why are both greater than equal to, like one can be 0 also, like
Yeah, so if one of them is 0, see the issue is the following. If k is 0, then then we have already proven that x, y, and w1 through wl are all distinct, no?
okay, okay.
Right? So therefore both of them must be at least 1. Okay, so a lot of things could be happening over here. Let's not worry about what is happening, but let's just focus on these three vertices, x, z, and y. Right? So consider the following paths, right? So how does P1 look like? So how does P1 look like? So therefore P1 is essentially the path x, v1, v2 up to what? Vi minus 1, z, vi plus 1 through vk, y, and then P2 is equal to x, w1, w2, wj minus 1, z, wj plus 1, wl, y. Right, so now consider the paths. Consider the following four paths. Right, so I'm just breaking P1 into two parts, and I'm breaking P2 into two parts. So let's call them something. No, let's call them Q1 is equal to x v1 v2 vi minus 1 z. Q2 is z vi plus 1 vk y, and similarly Q3 is x w1 through wj minus 1 z, and Q4 is z wj plus 1 through wl y. Right, so now what happens? Now if q1 not equal to q3, then this contradicts the minimality of m. Right, so we have found a pair of different paths, right, distinct paths between the same pair of vertices x and z, right? So this is not x1, yeah, so between the same pair of vertices x and z, but whose total length is smaller than m, right? So this is a contradiction to the minimality of m. Similarly, if q2 not equal to q4, then again this contradicts the minimality of m. Why? Because we have found two paths, two distinct paths, between the same pair of vertices z and y. So by the way, when I say q1 not equal to q3, I'm just saying that, okay, they're not completely the same, right? So they could have some overlaps and so on. I don't care. Okay. Yeah, Abhinav, I'm coming to you. Let me just finish the last sentence of this proof. Otherwise, what happens? So if q1 equal to q3 and q2 equal to q4, oh, did I write it properly? I think I messed up with the indices. I should have said Q1 equal to Q2 over here. No, did I write it properly? Yeah, Q3. This is Q2. Yeah, if Q1 equal to Q3 and Q2 equal to Q4, then what? Then we just have P1 equal to P2. Right, so there is a contradiction. Contradiction because we assumed P1 not equal to P2, right? So that is what we assumed earlier, I hope. Yes, so total length M, and I should have said over here P1 not equal to P2. Okay, Abhinav?
Sir, have we defined the equality of paths or walks?
I mean, how have we defined the paths, right? So we have defined paths to be a sequence of vertices, finally, right? Satisfying certain conditions. So when I say the two paths are equal, it means that the coordinate wise the sequences are equal.
So we can use this standard notation, right, in exams also.
Yeah, that's fine. That's fine.
Okay, thank you, sir.
Okay, Ramanuj?
I just after I posted my proof yesterday, that was incomplete, I guess, because I had to consider the case of the first few vertices of path P1 and
Yeah,
P2 being.
so your proof involved some the earliest Vi which equals to some Wj and trying to construct a cycle out of that, right?
Yeah, so it can easily be fixed though. Like you can say if the first
sure.
are the
Correct,
same,
correct. So I agree that it can be fixed. So, but the minor issue I have with that proof is it's also going to run into kind of complications like this. So, so I thought let me just present this. Okay, so I'm pretty sure you'll be able to fix it.
Yeah.
Okay, so now what? So now therefore, right? So this is a contradiction, right? So therefore, x, y, v1 through vk, w1 through wl are all distinct, right? So therefore, x, v1 through vk, y, wl through w1, x is a cycle. All right. Any questions before we go ahead? So I hope this proof looks okay now.
Sorry, sir, I have joined a bit late. What did we
Sorry?
prove just? So what did we prove just now?
So what were we trying to prove? We proved that if the graph contains two different paths from between the same pair of vertices, then it contains a cycle, right? So we started out with, right? So because the graph has two paths between the same pair of vertices, we said that S is non-empty, right? And because S is non-empty, we managed to we picked up the two paths between the same pair of vertices which have the least total length, and then we actually claimed that those two paths must actually kind of form a cycle. You can append first path to the reverse of the second path and get a cycle.
Yes.
Okay.
Okay, sir. Okay.
All right. So Shrimanti, yes.
So, sir, could we have made changes to the set S, what I was saying earlier? Would that
Okay,
have
yeah.
been
Let's come back to your
possible?
proof. What was your argument?
So could we have said that the set S consists of length P plus length P dash, where P and P dash are distinct paths in G with the same endpoints, and the second vertex should be different? Does this contradict something?
And the second vertex should be different. So you want to okay, so you are saying the second vertex of the first path must be different from the second vertex of the second path, and that's the way you are defining the set S. Okay, and then what do you do with this set S? You again pick the minimum element of S, right?
Yes, sir. The way you did, then we don't need this case.
Which case you don't need?
This the what you did today, like consider the following paths. But you
But
had
then
done
you'll
the
need this
previous.
case nevertheless, right? Shrimanti, you might end up in this kind of situation. Right, so the second vertices are different, but then there is some tail.
Is it trivial
So you
that
arrive at a
there are
contradiction. Yeah.
is it trivial that there are always two paths such that the second word, like I know it, there is always two paths such that the second vertex is different, but won't we have to prove that? Because like else you can just say two paths such that every vertex is distinct.
Yeah. So that needs some argument. Yes. So who is this? Is this Ramanuj? Yeah, Ramanuj. Yes, Ramanuj has a point. So Shrimanti, you will have to spend some sentences in proving that, okay, if you have two paths between the same pair of vertices, you have two paths between same pair of vertices which differ in the second vertex. Right. So there is a little, maybe a sentence of argument over there involved. Okay.
Yes, sir. So do I need to say then the second last vertex is also different? Like it could
Then
be like
still I
what
can
you
construct
said.
such an example. No, still I can construct this example. So second last vertex is different, first is different. Where is the cycle? That requires some work.
Acha, okay.
Okay. Okay, so what do we have now? So therefore we have that if a graph is graph contains a cycle if and only if it has two vertices and two different paths between that pair of vertices. Okay, so now what is the corollary of this? So corollary of this result is, which I'll leave for you to prove, is corollary graph is a tree if and only if there is a unique path between every pair of vertices, every pair of its vertices. Right, so I'm not going to write the proof. Does somebody want to quickly tell out this proof? Right, it's a corollary, so obviously you have to use the previous result and say why this is true. Again, it's an if and only if statement. One way is easy. Manthan, yes.
So if there we will prove by contradiction that if there is no unique path between any at least one pair, then it will lead to formation of a cycle, and the definition of tree suggests that it should be acyclic.
It should be acyclic, yeah. So tree is acyclic by definition, sure. Minor correction. So you're trying to prove that you just proved one direction. No, you just proved this direction. If the graph is a tree, then there is a unique path, right? And then the missing point in that argument is that when you say unique path, it means exactly one path, right? So you have to also address the other case where there is no path, which means the graph is disconnected, right? So then therefore it cannot be a tree.
Okay. Sir.
Right. So if there are two vertices which don't have a unique path, then either they have at least two paths, in which case you will get a cycle in the graph, or they have no path between them, in which case the graph will be disconnected. So therefore, in either case, it will not be a tree. Right. So that proves the left to right implication. What about the right to left? I think that is much easier. Right. So there is a unique path, right? So because there is a unique path, the graph is connected by definition. And because there is a unique path, there is no cycle also, right? So that's easy. So this I'll leave for you to write on the proof. Okay, cool. So now we'll come back to the two questions we had asked in the last class, right? And again, those proofs also I'm not going to do. I'll leave them as an exercise for you to figure out in your tutorial, right? So the questions were: suppose I take a tree and I remove one edge from the tree. Okay, so what do I get? So I think in the last class somebody already said that you'll get exactly two disconnected components, and I would like to make an addition to that by saying that, okay, you take any edge which has one endpoint in each of the component and you add it to the whatever is left out of that tree, you'll get back another tree, right? So the claim I'm trying to make is the following: claim, let Okay. ठीक है. So let me put it this way. Let G equal to VE be a tree, and let E be an edge in capital E. Then G prime is equal to V E minus this edge E has exactly two connected components. Further, if U and V are in different components of G of
Sir,
G
excuse
prime.
me.
Yeah, one second. Let me just finish this sentence. Then what? So then G double prime, which is equal to V, same set of vertices. I remove this edge E, and now I'm adding another edge, which is UV. Right, so this guy is also a tree. Yeah, somebody was asking something.
Yes, sir. Sir, is a vertex with 0 degree counted as a connected component?
Is a vertex with 0 degree counted as yes, it is. Yes, that single vertex by itself is a connected component. Yes, you're right. Okay, so what am I saying over here? You take some tree, you take any tree, right? You, let's say, disconnect. This is your G, right? So I remove this edge, let's say, and I get G prime, right? Which has two connected components, which is this is one component, and there's another component. And now I'm taking any two vertices U and V which are in different connected components. Let's say I take this as my U and this as my V. And now how am I constructing the graph G double prime? I'm taking the graph G prime, right? And I'm adding this edge, adding an edge between U and V. And now I claim that what I get back is another tree. Okay. So should I leave this for you to figure out for the tutorial? I mean, anyway, we are going to discuss it during the tutorial sometime, right? Okay. So this is what is called the cut property of trees, right? So this is called the cut property of trees, right? And the other question we asked in the last class was the following. Suppose I take a tree and now I add an edge which was not already present in the tree. What do you get? Obviously you create a cycle, but the claim is that you actually create exactly one cycle. You don't create more than one cycles out of this. And similarly, if I take any edge in that cycle and now I throw that edge away, I get back a tree. Right, so let me just write it down. Right, so the order in which you are performing these operations is different now, right? So you started out with the red tree, you added the blue edge, right? So the claim is that you create exactly one cycle, which is the case in this scenario. And now the other claim is I remove any one edge out of the edges in the cycle, right? I get back a tree. Okay, so yeah, so I hope it is clear what do I mean by edge in a cycle, right? So edge which kind of gets traversed, right? So we say, okay, side note, we say edge E lies on a walk, right? So V1 through Vm, if what is happening? If the endpoints of E appear as consecutive entries, consecutive vertices in the walk. Right, so I hope this was obvious. I just made it kind of explicit over here. Okay, so what is the claim that I'm trying to write? So the claim is the following: let G is equal to VE be a tree, and let UV be vertices such that UV is not an edge in G. Then G prime is equal to V E union E prime, sorry, E union what? E union the edge UV contains exactly one cycle, okay, up to order of traversing. I'll explain what I mean by this. Okay, so, and moreover, if E is any edge on this cycle, then what? So then G double prime is equal to the same vertex set. You have the edge set is E union UV, and now you are removing the edge, right? So this is also a tree. So what do I mean by up to order of traversal? So let's call these vertices something A, B, C, D, right? So I don't want to, when I say up to order of traversal, I don't want to say that A, B, C, D and A, D, B, C are different cycles. So I just want to say they are same cycle. Okay, whether I traverse it in the clockwise sense, anti-clockwise sense, I just want to count it as one cycle. Okay, is the claim, are the statements of the claims clear? If not the proofs, at least the statements. All right, so now I'm going to leave this. Okay, yeah. So by the way, this is called the cycle property of trees.
Sir, could you repeat what is meant by order of traversal?
Yeah, so basically I am saying that whether you traverse the cycle in the order A, B, C, D, A, or whether you traverse it in the order A, D, C, B, A, I want to count it as one cycle. That's what I mean by order of traversal of cycle.
Achha, okay, sir.
Yeah. Otherwise, you can never have a single cycle in a graph, right? Technically. And already, by the way, we already remarked that if you have a closed walk, then the cyclic shift of a closed walk is also closed. I mean, it's the same closed walk. Closed walk really doesn't have endpoints for us. So it's just a matter of convenience for us to write down it as an array of vertices that we kind of cut the closed walk at some point and then we write down the vertices. Okay, fine. So why did we at all mention this these two properties? So the reason is the following. Right, so central prominent problem that we'll study in data structures, call 106, and also in call 351 in the next year, which is the course on algorithms, is the following problem, right? So the input is the following problem. Input is the following. So right, so the problem is called the minimum spanning tree problem. Actually, let's make it explicit. Let's call it minimum weight spanning tree. Right, so your input is a connected graph. Let's say G is equal to VE and a weight function W going from the edge set to, let's say, the real numbers. Right, so every edge is associated with some kind of weight, or you can think of it as the length of the edge if you were to imagine it as a as a kind of map of a city or something. Right, so you want, okay, so you have a connected graph. By the way, yeah, I should have added this claim to the, sorry, I should have added this. So claim, right, so this is also for your tutorial, prove that if G is a connected graph, then there exists a tree which is a subgraph of G. Right, so such a tree is called a spanning tree of G. Such a tree is called a spanning tree of G. Right, so this is also for your tutorial. It's an easy another application of the usual well ordering principle. Right, so this is more of a practice of writing proofs using well ordering principle. Okay, what am I claiming? If G is a connected graph, which means there is a path from every vertex to every other vertex, then there must be a tree, right? So if it must be possible to select a few edges of the graph and create a tree. Okay, so it is possible to select a few edges of the graph and create a graph which still remains connected, but which now doesn't have any cycle. Okay, so such a tree is called a spanning tree of a graph, and then the spanning tree problem asks for the following. You are given a connected graph and a weight function. Yes, is there some question? Yeah, Prabal.
Could you please explain it again? The last spanning tree, what it is?
Okay, fine. So maybe I'll quickly explain by an example. Let's draw some graph. Okay. This is some graph, right? It's connected, right? So now I want to claim that there exists a tree, right, which is a subgraph of this graph, right? So look at this tree, for example. Right, so the green edges form a tree, and it is a subgraph of the graph represented by the red edges. Right, so that's what I want you to prove, that every connected graph has a subgraph which is actually a tree. Is that okay, Prabal? Yeah, Somil?
Yes.
Somil?
So we require that the subgraph should have all the vertices of the original graph, right?
But as soon as yeah, you're right. Yes. Yeah, so let me mention that. Yeah. Prove that if G equal to VE is a connected graph, then there exists a tree on vertex set V, which is a subgraph of G. So the vertex set of the tree is the same, and it maintains connectivity, and furthermore, it kind of deletes all the cycles in G. So it does not, this subgraph does not contain a cycle. Okay, so what is the minimum spanning tree problem? You are given a connected graph G, and you are given a weight associated with every edge, right? So now you want to output a spanning tree of G with minimum weight, where weight of a tree is the sum of the weights of the edges in the tree. Okay, and then for this problem, a simple kind of greedy algorithm works. You keep on adding edges, sort the edges by increasing order of weight, and keep on adding edges as long as you don't get a cycle, right? So this kind of algorithm works, and why does it work? The reason is are these cut and the cycle, cut property and cycle property. Okay, so let me leave it at that. So you might do this either in data structures or in the algorithms course. So let me not do it right now. Okay, so this just for your information, FYI. Okay, so should we move to something different from trees now? Or let me wait for a couple of seconds in case there are questions. Okay, all right. So we are moving to something completely different now. If you are asleep, this is a good time to wake up and regain your attention. So the problem that I'm going to discuss is the following, right? So let us copy a diagram which I had drawn earlier. Right. So what is this? Right. So as most of you, or maybe some of you might already know, I like to run. Right. So I usually go for a run, obviously in the IIT campus. I don't go outside, right? Because there is a lot of traffic outside. So let's imagine this is the map of the IIT campus. Okay. So so let's say let's mark the junction points between the roads, right? So you have several junction points and then you have roads between them, right? So obviously you can represent this as a graph, right? So I hope, yeah, and so on, right? So now the problem is the following. Let's say I stay at some point. Let's say I stay over here on campus, okay? And now every evening I want to get out and I want to go for a run, but the constraints are as follows. Firstly, I don't want to repeat traversing any road, right? I don't want to run on any given road twice, right? Otherwise that becomes kind of boring to me. Other constraint is I want to maximize the distance that I run, right? Obviously, right? So therefore I want to figure out whether there is a way that I can start from my home, right? I can start running from there, traverse all the roads in the campus and come back to where I started. Okay, you are not allowed to repeat a road, right? So if you traverse a road from in the direction A to B, you are also not allowed to go traverse it in the B to A direction now. You can traverse every road exact. Okay, so basically you need to traverse every road exactly once. Is this possible if this is the map of the campus? So is it clear what I'm looking for? Aniruddha, yes, I'll come to you. But before that, if there are questions about if something is not clear about what kind of thing I'm looking for, then you should ask them first. Okay, so apparently, Vedant, do you have a question or do you want to give an answer?
No, sir. I wanted to give an answer.
Give an answer. Okay, so let's give Aniruddha a chance earlier because he raised his hand before Vedant. Yes, Aniruddha.
So it's not possible because there are vertices of odd order. So if we have to odd degree, sorry, yeah. So if we enter those vertices, then we have to leave those vertices as well. And if you have an odd degree vertex, then you'll enter it, and you will have to traverse one edge twice. That is leading out from that vertex.
Yeah. So Aniruddha is saying that these odd vertices are the reason behind the problem, right? So as long as I have these kind of odd vertices, right? So it's just impossible to kind of enter, right? So if you look at the edges incident on an odd vertex, odd degree vertex, it is just impossible to traverse all of them exactly once. Why? Because every time you enter the vertex, you also need to leave it, right? So yeah, anything else? Vedant and I don't know who else raised their hands. Did they want to say anything else?
No, sir. I had the exact.
Srimanti, yes, Srimanti, your hand is up.
Sir, if we started from an odd vertex, then it could be possible. It was the only odd vertex. And we
Shrimanti, you want to come back to the same vertex once again. You want to end your run at the same vertex.
Yes, sir, but then I can again go out. Oh, achha, I want to come back there, not A to B. Okay, okay.
Yeah, I want to come back home, right? After the run.
Excuse me,
So
sir?
I don't want to run around the campus and then go from my home to office, right? I want to come back home.
Okay. Fine.
Yeah.
So you want to come back, and plus you have to cover all vertices, or you just have to cover maximum distance that is possible by.
No, I want to. Okay, so so that's a completely different problem. If you are asking how should I cover the maximum possible distance for this graph, that's a completely different problem. Let's not worry about it. Let's try to just figure out.
I am asking the constraint. The constraint is that you have to cover all the vertices, or you have to cover the maximum distance.
No, I want to cover all the edges exactly once.
Okay.
Right. I want to cover all the edges exactly once, right? And why do I want to not repeat an edge? Because that becomes boring for me. And why do I want to cover every edge? Because it's my attempt to traverse the maximum distance, right? So if I'm not able to cover all edges, then I'll start worrying about what is the maximum distance I'll cover, right? But before that, let's try to figure out whether it's possible to cover all edges or not. If that is possible, then the answer is obvious, right? So the sum of the lengths of the edges is the maximum distance I'll be able to run. Sum of the lengths of all those routes. Okay, so now I hope it is clear that for such a trail to exist, every vertex must have even degree. Okay, so let's try to construct let's say underground roads in the campus so that every vertex has even degree. So right, so this is odd. So let me draw an underpass from this vertex to this vertex. Which else is odd? This is odd. What else is odd? This is odd. So let me construct an underpass between them. So I'll include these green underpasses also as I'll count them as roads, and I want to traverse all of them exactly once. Right. So are there more odd vertices? There is one over here. There is one over here. Chalo. So let's draw a path over here. Where else? There is one over here. There is one over here. So let's draw this kind of a path. Let me add a vertex over here so that you don't have two edges between the same pair of vertices. What else? Is that all? I have one over here and I have one over here. Chalo, let's pair them up. I hope that is all. What is this? 1, 2, 3, 4, 5. Oh, I have one over here and I need to pair it up with something. Yeah, either here. So I hope everything has an even degree now.
No, so there's one left.
There's one left? Okay, one sec. Let me draw this properly. Which one is left?
Sir, the one you joined, the diagonal to the one you joined just now.
Diagonal, acha, this one. And then there should be another one left, right?
Just above it as well, I think. 1,
2, 3, 4. No, this is 4.
Sir,
no, sir, he's saying just above the one you joined just now.
Oh, this is this one. 1, 2, 3, 4. No.
So the edge of the smaller cube. The vertex.
So diagonal to your house.
Oh, awesome. Good. Right. So now I hope this is fixed. Right. So now by creating these tunnels, underground tunnels, I have made the degree of all vertices to be even. Now is it possible? Necessarily possible. Right. So you might want to take this as an offline question, trying to figure out a tour for this graph if possible. Right. But then let's come back to the Viraj. Yes.
So I think like even if all have even degree, I think it's still not necessary. Like sir, I thought like just join two squares at one edge. And then starting at.
Yeah, you have two squares and then what?
Join them at one edge, just one edge.
Like this? But then you have two odd degree vertices.
Okay.
Sir, no, not saying it. Sir, draw in a square, and on the edge of a square, draw another square. He's saying this, I think.
On the edge of like this?
Yes, sir, like this.
But
no, just one edge common. Just one edge common.
Yeah, in this one edge is on.
No, not one edge. I mean one vertex. Sorry, I'm saying edge. Sorry.
Only one vertex common. Acha.
Yes.
Like this.
No, in one vertex case it would be possible.
Yeah.
How
Sir,
is it
but in
possible?
one edge
We won't
case,
be able to
it's
come
not
back,
possible.
right? We're not able to come back, right?
Why you can
No,
traverse?
we are able to
traverse
come back.
edges, no?
So, but we are coming back to one edge, right? The edge which is at one vertex, right?
Yeah.
If we
I don't
start,
understand. What's the
if we
difficulty?
keep the start point not at that one, I'm saying if we keep the start point, we don't keep it at that
Wait,
common
let's
edge
name the
vertex.
vertices and then come back to you. Let's
Yes.
let's name the vertices A, B, C, D, E, F, G. Yeah. So what are you saying now?
If we start at A, then it is not possible.
No, it is
Why
possible.
A,
Sir,
C,
A, B, D, F.
C, D, B, A?
Okay, okay, yeah. Okay. Sorry.
Sir, but in above case, sir, in which one edge is common, means a square
This
and a
one?
new square is drawn on one edge. Yes,
This
sir.
one?
Yes,
So then
sir.
you have two odd degree vertices.
Okay, there are odd degrees.
है ना? Viraj, your
Yes.
hand is up.
Sorry.
Yeah. Okay. Fine. Fine. So let's try to define all these notions properly. Vedant?
Yes, I think it's always possible to find
Okay,
a
you
path.
think it's always possible. Okay, cool. Manthan?
So can you please explain how Aniruddha explained that odd degree cannot let? I mean, what was the reason he said? I mean,
Okay, so the reason is the following. Let's say you have an odd degree vertex. Let's say its degree is like 5 or something, right? So you want to traverse all these edges, right? So if you traverse one edge in this direction, in the incoming direction, you need to pair it up with the next edge that you traverse must be in the outgoing direction. Right, so you need to get out of this vertex.
Okay, so got it. Yes, got it.
Okay.
Yes.
All right. So cool. Okay, let me just delete this slide. All right. So let's define these notions properly, and then we'll figure out whether it is always possible if the all the degrees are even. Okay. So definition. Right, let G be a graph. Okay. Okay, so let me add something over here in this definition. We say that G vertex edge E lies on a walk blah, or equivalently we'll also say the walk traverses the edge E, or equivalently the walk traverses the edge, right? So E lies on the walk and walk traverses edge E, both are same thing. Okay, so is this some little words that I'm adding to your vocabulary? Let G be a graph. Walk is a walk in G is said to be an Euler walk if it traverses every edge of G exactly once. Okay, and similarly a closed walk in G is said to be an Euler tour again. The condition is the same if it traverses every edge of G exactly once. Right, so what exactly was I looking for in this graph? I wanted an Euler tour, right? I wanted to start from some vertex and end back in the same vertex, right? So in an Euler walk, you are not required to end your walk in the same vertex. You could end it in a different vertex, right? So I could start from my home, traverse all the edges and go to my office. That's fine. Okay. So my question is, the question that I was trying to ask is, when does a graph contain an Euler tour? Okay. And then as somebody remarked, right? So if a graph contains an Euler tour, first of all, yeah, so the remark was that every vertex must have even degree, right? And then there is one more condition which you didn't specify. What is it? Right? So there is another condition which is implied by the fact that the graph has a Euler tour, apart from every vertex having even degree. Yes. What is it?
Connectivity.
Connectivity, yes, but you're almost there. But the reason I'm saying almost is
cyclic.
Cyclic? This is not cyclic. What do you mean cyclic? What do you mean cyclic? I don't understand. Okay, connectivity is almost correct, and the reason I'm saying it's almost correct and not exactly correct is I could have something like this, right? So I have all vertices of even degree, let's say degree 4, but I could have other isolated vertices. This is not connected as per our definition, but then this has a Euler tool. Okay, so the condition that I'm really looking for is it should have exactly one non-empty connected component. Right, that's a better way of saying it, or exactly one component which is not an isolated vertex. That's another way of saying it. Is that okay?
So like in our definition of connected, it was this, right? That for every pair of vertices, we can have a path between them.
Correct. That was the definition of a connected graph.
So like, how does it satisfy?
How does what satisfy?
Like you said that this is a connected graph according to our definition.
No. This is not a connected graph, I said. According to our definition, this is not a connected graph, but still it has an Euler tour. Why? Because it has exactly one connected component which is not an isolated vertex. Okay? Yeah. Right. So observation, let me just note this as an observation. Yeah.
So
yes,
a closed walk in G is said to be Euler tour if it traverses every edge of G. Oh, sorry, edge. Fine, sorry. Like every vertex should not be covered, right? It may not be covered.
Yeah, that is not a constraint. So if you have an isolated vertex, fine. I don't mind. Okay. Yeah. So observation. If G has an Euler tour, right? So by the way, little note about Euler. So this is the name of a mathematician. His name, full name is Leonhard Euler, and he was an 18th century Swiss mathematician, right? So let me just note it down over here. Right. So this named after mathematician Leonhard Euler. Right, so EU is pronounced as Oi in German, so that's why it's called Euler. Okay, so G has an Euler tour. If G has an Euler tour, then condition number 1, every vertex of G has even degree, and condition number 2, G has exactly one non-empty connected component. That is exactly one connected component which is not an isolated vertex. which is not an isolated vertex. Okay, so these two conditions are necessary for the graph to have an Euler tool. Now the obvious question is, are they sufficient? Right? So if a graph satisfies these two conditions, does it necessarily have an Euler tool? So somebody said that, okay, somebody said that these conditions are sufficient, right? Somebody made that conjecture. Who was it? Could you raise your hand? Yeah, Vedant thinks that if these two conditions are satisfied, then G must necessarily have an Euler tool. Vedant, do you have any intuition of why this could be true? Vedant?
Sir, I think that as long as we don't come to a neighboring point immediately to our starting point, we can just keep going. I don't have a concrete proof as of now. It's just your intuition.
Acha. So we'll do the concrete proof. Okay, so the claim is the following. The theorem is the following. Let G be a... Okay, let me state it in this way. Let G be a graph in which every vertex has even degree. Okay. G be any graph in which every vertex has even degree, then okay, if G has exactly one non-empty connected component, then G has an Euler tool. That is the claim we are going to try to prove. So, Amil, yes?
Slightly pedantic point, but would we say that the empty graph has an Euler tool? Like it
technically
has
not, because we didn't define an empty closed walk, right?
Okay.
Yeah, so yeah, minor corner case. Yeah, but good that you brought this up. Okay, so cool, right? So this is the claim we are trying to prove, right? So let us do some background work before we actually go into proving this claim, right? So G has exactly one non-empty connected component, fine, and G has every vertex in that connected component has even degree. So any immediate conclusion that you can draw out of this, right? So you have this connected component, right? So this non-empty connected component. And in which every vertex has even degree, right? And it is non-empty, and it's a connected component. Does that tell you something about the existence of some kind of an object within that connected component from whatever we have learned so far? Yes, Shrimanti?
Sir, can we say that the number of edges will be even then?
Number of edges will be even. Is that true? I am not sure. Why is that so? Number of edges is even.
So like summation of all the degrees should be equal to 2 times the number of edges.
Edges, sure. So the left hand side is even, the right hand side is even. You can cancel out a 2. What does that tell you about the parity of number of edges?
Consider the pentagon. No, so
it can be a pentagon or a triangle.
Consider so the pentagon, is that an example? Pentagon is going to have how many edges? 5 into 4 divided by 2. That is even, no?
No, sir. A simple pentagon. No diagonals.
Pentagon.
Triangle.
Yeah. So obviously, yeah, triangle. Yeah, triangle is an example, right? Okay, fine. So that conjecture does not seem to be true, right? So what? Just the fact that the graph is connected and every degree is even. What does that tell you, Vedant? Yes.
That there is no leaf.
There is no leaf. True. Fine. Anything more? Riya?
Cycle.
Cycle,
Graph
yes,
is
you are
actually
So
right.
it's,
Yeah.
cycle.
it's connected. It will be a cycle. Yeah.
Yeah, there will be a cycle, right? And why is that so? Could somebody give a concrete justification of why will this connected component contain a cycle?
So we had done this previously that if there is a connected component and there are no leaves, so there should be a cycle.
And there are no acha, yeah. So that is okay. Fine. Sounds good. That's a good justification. Other possible way of saying it is, look, if the degree of every vertex is at least 2, and therefore the total degree is at least the number of edges, and therefore it cannot be a tree, right? And yeah, it's connected, and the number of edges is more than n-1. So therefore it cannot be a cyclic, which means it must contain a cycle. That is another way of putting it. Vedant, your hand is still up. Did you want to ask something? Say something?
No,
Achha, no. Okay, cool. Right. So now we have concluded that this connected component must contain a cycle. Right. So let's draw that cycle. Fine. So clearly this cycle by itself need not be an Euler 2, right? So it could have tons of other edges. But let's try to make some progress. Suppose I remove this cycle from the graph. Right, so I take this connected component. I have figured out that it has a cycle. I found the cycle. I found one cycle, and I removed this cycle. What kind of graph will I get? Yeah, Rishabh.
You would get a smaller graph with even number, even degree, but connectedness would be an issue.
Okay, so yes, clearly you will have a graph with fewer edges. That is true. The degree of every vertex will still be even. Why? Because every vertex which is on the cycle is losing 2 edges, and every vertex which is not on the cycle is not losing any edge. So degree will still be even, but the only issue could be that this cycle, removing of this cycle might actually disconnect this connected component into several parts. That is true. Okay. So now, does this suggest some kind of an idea? What could we do?
Can you repeat what you have done?
Induction type, induction kind of.
Yeah, somebody is asking me to repeat, so let me just repeat it first. So yes, we figured out that this connected component must contain a cycle. Now my question was, suppose I remove this cycle suppose I remove the edges involved in the cycle from the graph. What kind of a graph will you get? So the claim is that firstly, the degree of every vertex even in that graph is going to be even. Why? Because every vertex which is on the cycle is losing 2 edges, and every vertex which is not on the cycle is retaining all of its edges. Okay, so every vertex is still going to have even degree, and yeah, so the only issue is that, okay, by removing this cycle, the graph could actually get disconnected into several parts. That is a possibility. Okay, so Somil, yes, your hand is up.
No, I wanted to tell an idea. You asked for an idea, right? After this.
Yes.
Yeah.
Tell an
Okay.
idea.
So what we can do is, it's sort of an algorithmic proof only. So what we do is, like, we take the cycle and we start at any vertex and consider the connected component it is in the new graph. Let G dash be the graph after removing the cycle. So I consider the connected component V1 is in G dash. So either this connected component is just V1 itself, then we do nothing. Otherwise, by induction, we can say that induction on number of edges, whatever. Number of edges works. Yeah. So we traverse the in this connected component starting at V1, come back at V1. Then you traverse the edge V1, V2, and if V2, then you come at V2. Then either V2 was or has already been in a connected component before, that is, it has already been in V1, in which case you just move on. Otherwise, you again cover the connected component of V2 using an Euler 2 starting at V2. Then you go at
induction once again. Good. Okay.
Yeah. So basically, when you arrive at Vi, you check if Vi has already been covered in a the connected component in which Vi is in has already been covered in one of the processes at the previous I-1 vertices. Otherwise, you cover its connected component and move on.
Okay, good. Very nice idea. Yes, that is exactly what we are trying to do. There were other hands up. I believe they also had the same idea. Yes, Ramanuj.
I have the same idea, but in this I had like a little doubt. So in this, if we are using induction and we like first choose an arbitrary cycle, so we have to use, first of all, we have to use strong induction, obviously, and secondly, is like induction on the number of edges, will it work here or will it be something?
Why not?
Okay, it should work.
Yeah. Okay.
Because okay, whatever. I think it would work then.
Okay. So the only issue that you need to address is the following. So, I mean that's a kind of trivial issue, but that needs to be addressed is the following. So suppose I remove this cycle, and I have a connected component which does not have even one vertex on this cycle. Then what? Then when are you going to traverse it? Somil?
I think that won't be possible because like you initially like take any vertex in that connected component. Okay, so is it okay, so take any vertex in that connected component and then you join it to a vertex of the cycle. Let's say the vertex in the connected component is V and the vertex on the cycle is U.
Nice. Okay.
Then you know that U is not in the same connected component as V in the new graph G dash. So, but it was in the same connected component in the original graph G. So then there must be, so then take a path from U to V to U and consider the first edge which occurs in that path and it wasn't part of the connected component of V in G dash. Then that edge has to be part of the cycle. So that
Very
means
nice.
you already reached
Very
vertex.
nice. Very nice. Awesome. Okay. So let's put together these ideas and write it into a proof. Okay. So let's write down the proof of these two lemmas. First lemma which claims that there is a cycle, and second lemma which claims that okay, if you remove that cycle, you will get several disconnected components, but every disconnected component is going to have at least one vertex on the cycle. Okay, and then once we write these two lemmas, then we'll prove this theorem by induction on the number of edges. Okay, so that is the plan. Let's see whether we are able to finish it today.
Sir, what did you ask Somil the last point? Like, what was the claim? Like, what
The question is the following. Well, I figured out there is a cycle in this connected component. I removed that cycle. The connected component got disconnected into several smaller components. Right? What if there is one connected component, whether there is one of those smaller connected components which does not even have one vertex on the cycle? When are you going to traverse it? That was my question. When are you going to take care of the edges of that connected component? Okay. Right. So, but then Somil claimed that that is just not possible, and rightly so. Okay. So, yeah. Let's see whether we are able to finish it today. Otherwise, we'll finish it in the next class. We don't need this now. Okay. Right. So claim. Let G be any graph in which every vertex has even degree. If G has exactly, or let me say, if G has at least one non-empty connected component, then G contains a cycle. Let G be any graph in which every vertex has even degree. If G is non-empty, let me just say it that way, then G has a cycle. G is non-empty, then G contains a cycle. And then the short proof which somebody gave was what? So every vertex, what was it? I think Shrimanti, you said, no? Shrimanti, I think you gave the proof of this, right?
No, sir, it was Ria.
Ria, sorry, Ria.
Yeah, sir, I had said that since there's a connected component and since all degrees are even, so we don't have any leaf. That means there must be a cycle.
Good. Yeah. So, okay, and then what did you? So you use the fact that every acyclic graph has a leaf, right? So yeah, proof. Yes. So every vertex has even degree, non-empty. So therefore, right. So what? Right. So G does not have a leaf. But and G is non-empty. And when did we prove this? Was it the last lecture or the one before that?
So the one lecture 8. The one
lecture 8. Are you sure?
Yes, sir.
Okay. So therefore, by a result from lecture 8, G contains a cycle. Cool. So the other claim is the following, right? Let G be any graph in which every vertex has even degree. What else? Do we need that every vertex has even degree? I don't think we need it. Let G be any connected let G be any connected graph. Let me put it that way. Connected graph, and let C be a set of edges forming a cycle, right? G equal to VE, then G prime is equal to V E minus C, then every connected component of the graph G prime is equal to V and edge set minus C contains a vertex on the cycle C formed by C. Okay, what is the proof? Right, so G is connected, so C is right. So let V be a vertex on the cycle formed by C, right, and let K be a connected component of G prime, right. So let U be a vertex of K, right. So G is connected. Since G is connected, there exists path, right? Path of the form u equal to, let's say, w0, w1, wm, which is equal to v in G, right? So we know wm lies on the cycle, right? So there must be some earliest vertex which lies on the cycle. Let wk be the earliest vertex on the earliest vertex that lies on the cycle, earliest vertex of the path that lies on the cycle. I hope the meaning of earliest is clear. What I mean is the minimum k such that wk lies on the cycle. That's all. Okay, so then what? Right, so then all the edges w0, w1, w1, w2, wk minus 1, wk are present in G prime. Right? Why? Because w0, w1, w2 up to wk minus 1, none of them lie on the cycle. So there is no question of removing any edge incident on them. Right? And therefore wk lies in, right? So therefore wk is a vertex of k, is also a vertex of k. Why? Because u is a vertex of k, and there is a path from u to wk in this graph G prime, right? So therefore wk also must belong to the same connected component as u, which is k. Right? So therefore wk is a vertex of k which lies on, and wk lies on the cycle. Is that okay?
No, so could you please explain? I did not understand anything.
Okay. Sorry? Arin, yes?
Explain the proof of this claim again.
Okay, fine. Okay. So you have removed some cycle C, right? So this is your cycle C, right? And now the graph got disconnected into several connected components, right? So suppose this is some connected component K. Okay, so suppose U is a vertex in this connected component. I want to prove that this connected component must touch this cycle somewhere, at least in one vertex, if not more. Right, so what do? I take any vertex on this cycle, let's call it, we called it what? We called it V, and I consider the path going from U to V, right? The original graph is connected, right? So there is a path from U to V in the original graph. Did I say that in the, there exists a path? Path in G. Okay, so let's look at this part. Yeah? Yeah, is there a question? Arin, yes?
No, sir, no question. Got it.
Achha. Fine. So let's look at this path. Right, so something could happen. Okay, so now I'm saying that, right, so the last vertex of this path is on the cycle. Right? So now look at the earliest vertex of this path which lies on the cycle. Let that be wk. Okay, it could be wm itself, or it could be some earlier vertex on the cycle. Right? So this is my wk. Now all the vertices on this path which are before wk are not on the cycle by definition. And because they are not on the cycle, right, the removal of the cycle does not remove any edge incident on them. Right, so all these edges are retained in, so these edges are retained in G prime. And now because these edges are retained in G prime, you have a path from U to wk in G prime. Right?
Okay,
and Yeah, so therefore Wk must belong to the same connected component of as U, which is K. Right, so every such connected component is going to have some vertex where it touches the cycle. Okay, so we have like 9 minutes. Let's see whether we can do the proof. Otherwise, if we don't manage to finish it today, we'll revisit it in the next lecture using these two claims. So yeah, these two claims really kind of make the remaining proof obvious. Right, so let's recall the theorem once again. Let's write down copy the statement of the theorem on the next slide. Let's give them some name. Let's call this claim 1 maybe. Oops. Let's call this claim 1. Let's call this claim 2. Okay, so now proof by induction on the number of edges. By strong induction on the number of edges. Base case, if number of edges is 0, then right, so then the condition G has exactly one non-empty connected component is violated. So the claim is true. Right? P implies Q, statement of the form P implies Q is true if the statement P itself is false. Right. So inductive case. Suppose number of edges is greater than 0. Right. So now what do you have? By claim 1, the graph contains a cycle. G contains a cycle. Say, let's call this cycle something. Let's call it V1, V2 up to Vm, and then V1 once again. Okay, let C be the edges involved in the cycle, which is V1, V2, Vm minus 1 Vm, and Vm V1 be the set of edges traversed by the cycle. Okay, then what? Let G prime be equal to the graph, right? So let G be equal to VE, right? So let G prime be equal to the graph V E minus C. Okay, so so what? So now G prime. So by claim 2, what do we say? What do we have? So by claim 2, every connected component of G prime, connected component K of G prime has a vertex, let's say U capital K, in the set V1 through Vn. Right? That's what claim 2 tells us. Is everything okay up to this point? Okay. So now every vertex of every connected component K of G prime has even degree. Right, and now we have, right, so the number of edges of this connected component is strictly less than the number of edges in the graph, right? So number of edges of K is strictly less than number of edges of G. So therefore, by induction hypothesis, right? So K has an Euler tour, right? So K has an Euler tour. So let's reorient the Euler tour so that it starts and ends with the vertex UK, right? Say UK and then some, what should we call this? Right, WK1, WK2, blah blah blah, and then you come back to UK. Okay, and this happens for every connected component K. Okay, so now what do we do? So consider the cycle V1, V2, Vm, V1 for every connected component K of G prime. Say, okay, let's give this some name. Okay, let's call this tour some TK. Okay, so for every connected component K of G prime, right? So replace one occurrence. Replace actually. Yeah, so there is going to be an exactly one occurrence of U except for the first and the last vertex. So let me, yeah, fine. Let me just actually write it in this way. Let replace one occurrence of vertex UK in the cycle by the walk TK. Right, so what we know, right? So this gives a closed walk in G, right? And then, but we know every edge of G is traversed by exactly one of C and the UKs and the TKs, right? So therefore, let's call this walk something W. So therefore, W is an Euler tour. Okay, so we are almost out of time. Any quick questions? If there is a need, we'll visit this once again in the next class. I don't mind doing that. But yeah, we have 1 minute for questions, if any.
Sir, what was the UK we had taken?
What was the UK you have taken? Wait. So yeah, every connected component K of G has some vertex UK in the set V1 through Vm. All right. So if there are more, we choose one arbitrarily. Doesn't matter. Right. So every connected component touches the cycle. You just pick one vertex which is common to the connected component and cycle and call it UK. Is that fine?
Yes, sir. But we aren't mentioning that.
That's what I have written. No, every connected component of K of G prime has a vertex, let's say UK, in the set V1 through Vm.
Okay. Okay, sir.
Yeah. All right. So time is up. So we'll meet each other on Thursday. Chalo, see you. Class is over.